In the previous section, we learned how to take the physical space around our geometry, like the flow video you saw, and convert it into a clean computational domain. We said we must extract key dimensions from the problem, and then define the full CFD domain properly. Step 2. Block decomposition of the computational domain. Now in this section, the next step is we must divide the computational domain into blocks. Because we want to use BlockMesh, and BlockMesh needs a clear block structure so it knows how to build the geometry and how to generate the mesh based on that structure. Our block layout, 8 blocks. For this square cylinder case, I chose a simple and practical block decomposition. 8 blocks total. This is one of the simplest clean block layouts you can use around a square obstacle. Of course, you can increase the number of blocks later. More blocks usually means more control over mesh refinement, potentially higher cell quality, but also more complexity in setup. Here, I name the blocks from block B0 all the way to block B7. Defining and numbering the vertices. Once the blocks are defined, we must define the vertices that form those blocks. I start numbering from point 0, located at the top left corner of block B0, and continue until point 15. So now, in 2D, we have 16 points that define the full block layout. Extruding to 3D Z direction. But the flow we are solving is essentially 2D. So what do we do in OpenFOAM? We create a thin 3D domain by extruding the 2D points in the Z direction. That means every point from 0 to 15 gets a corresponding point in the Z direction. So, point 0 becomes point 16, point 1 becomes point 17, point 15 becomes point 31. So in total we now have 32 points. And this is a key concept. The new points have the same x and y coordinates as the original ones, and the only difference is their z value. For example, point 24 corresponds directly to point 8. Same x, same y, only shifted in z. How we extract coordinates from the domain dimensions. Now, using the domain sketch and the dimensions we defined in the previous section, we can compute the coordinates of each point. For example, look at point 9. In the x direction, it is 5h downstream. In the y direction, it is at 6h. Why 6h? Because we had 5.5h from the square center to the top boundary, plus 0.5h from the center to the top side of the square. So, y equals 6h. And for all points in the 2D plane, z equals 0. So, point 9 equals 5h, 6h, 0. You can do this as a very good exercise. Try extracting the coordinates of all points from 0 to 15. What we achieved in this section. So now we've done 2 important things. We divided the computational domain into 8 blocks. We extracted and defined the coordinates of all vertices, 32 points total after extrusion. Next section. In the next section, we will start writing the most important file for this step, BlockMesh dict. We'll write it together, run BlockMesh, and generate the mesh for the square cylinder domain.